Okay, we're supposed to first complete this table, and one of the things that kids sometimes struggle with here is when we get something like this, they say, oh, what is 31 and one is 15? I know one's the atomic number, and I know one's the atomic mass. And if you just kind of think about that for a second, there can't be more protons than there is mass. So there's no way that there's 31 protons and the mass is 15. So if you just kind of think about that for half a second and understand that, then you'll know, okay, 15 must be the number of protons because that's also the atomic number, and the mass number is 31. And I can kind of verify one of those numbers at the very least with the periodic table. If I look for phosphorus, it's right there, and it has atomic number of 15. And remember, this is the average atomic mass. This isn't all of the atomic mass, so I can't really use that to verify the mass. Okay, that mass number will always be a whole number. It'll always be some isotope of phosphorus. Okay, so now it's just a matter of figuring the rest of this out. Well, it doesn't have a charge. There's no charge here, so we're going to assume that that's 0, which means there must be 15 pluses and 15 minuses. And that must mean 16 neutrons. And I'm going to go ahead and do the next one. Well, this one, I know that aluminum is 13 because that's the smaller number. 13. The mass is 28, which means that the neutrons, which are the only other thing with significant mass, is 15. And then the protons and electrons. Well, the protons can't change. So if I put 13 of these, I'm just going to put them in groups of 5. If I put 13 of these, that's 13 positives, right? And now I've got 10 negative. In order to get to plus 3, well, I must have canceled out 5 of those. If I cancel out another 5, now I'm left with just a plus 3. So that must mean that there are 10 electrons. I'm going to go ahead and fill in the rest of the chart. And you can pause it on that screen if you want, just to make sure that you got those right. Boom, like magic, it's all done. Quick thing, if there's no charge, again, if there's no charge mentioned, then we're assuming that the number of protons and the number of electrons are the same. If there is a charge, well, that must mean that the protons and electrons are not the same. For instance, here, this has a 7 protons. That can never change, but it has 10 electrons. It's got 3 more negatives than it does positives. If you want, you can pause it here. I'm going to move on to number 10. Okay, number 10 here says a certain element has 2 isotopes. One of those has an abundance of about 72% with a mass of about 85. The other one has a mass of about 87. Calculate the average mass for this element. Let's go ahead and we're going to say something that we know to be true from these statements that we just got. We know that for every 100 isotopes, 72.15 of them weigh 84.9118 grams, or I should say AMUs. And the rest, so that's going to be 72.15 minus 100. I know it's out of 100%. So that'll be 27.85 of them weigh 86.9092 AMUs. And we can simplify this a little further, and we talked about this in class, is that 6 times 10 to the 23rd of these isotopes, there's a bunch of numbers here, but that the relationship between this number and this number, those two numbers must always equal this number, no matter what unit we have them in. Okay? So I'm going to just simplify this a little bit further. I'm going to say for every 1 mole of isotopes, 0.7215 moles weigh 84.9118 AMUs and 0.2785 moles of them weigh 86.9092 AMUs. Okay, and then I'm going to just go ahead and I'm going to say, all right, well, I want to know how many grams there are. Well, I know that this is going to be times 84.9118 grams because that's how much a mole of this particular isotope weighs. And I'm going to say that this one is times, and this is a little bit different than what we've done before, 86.9092 grams. Okay, and remember before we said that these two numbers always added up to this number. Well, that means that these two numbers must add up to 1 mole of isotopes. So if I add those two numbers up, and this is where a calculator comes in real handy here, it comes out to be, calculator only comes in handy if I type in the right numbers, 85.46 grams. Now that number falls somewhere between my two original numbers of 85 and 87, and it should definitely be closer to this one because there's more of them. So that's kind of my little check for that. Okay, last problem, same basic setup. This time though, instead of just 2 isotopes, now we've got 3 isotopes to contend with. So we just have a longer for every statement. So we're going to say for every 100 isotopes, because again, these are percentages, 78.70 of them weigh 23.985 AMUs. 10.13 of them weigh 24.986 AMUs. And 11.17 of them weigh 25.983 AMUs. Okay? And if I add all of those percentages up, all 3 of these, I should get about 100. And I do. So, now, again, we're just kind of changing this for every statement into, now we're saying for every 1 mole of this magnesium, 0.787 moles are 23.985 AMUs. 0.1013 are 24.986 AMUs. And 0.1117 are moles. These are all moles. Are 25.983 AMUs. Okay? And then I'm just going to multiply each one of these by their number of AMUs, which is also the molar mass. And since I'm using moles, I can do that. And there's the 3 values that I get. And when I add all of those together, and again, the reason I can do that is because these up here added together. So that must mean that no matter what unit this is down here, they must also add together. So just stick a unit on that, 2.53, and 18.88 is 24.31 grams. Now, does that answer make sense? Well, most of them were about 24. And only a few of them, about 20%, were more than 24. So this number should be more than 24, but it's not going to be 25 or 26. Okay, hope that helps.